I'm gonna get guys from Clear Life. Have you had a dress? Yeah, that's me too.
I love that show. I've seen that. I'm gonna remember that.
So how's this probability coming?
Oh, yeah.
Feeling good about it? Again, here's the upside. Test is not tomorrow. Okay?
What's it going to be?
No.
Okay.
But there's lots of time to get this under your belt. The big thing I need from you guys is just questions, like to really help me know, engage what you're getting, what you're not getting, so I can troubleshoot those things. You're going to have lots of time to review. Believe it or not, throwing everything out there. So literally we got Thursday, Friday. I forget when we bumped it back to. Thursday, Friday, Monday, Tuesday, Wednesday. So literally we're kind of on a 5-day review right now. But I just want to keep throwing more and more stuff at you. You've seen probably the worst of it. Well, there's one thing I don't know that we've really addressed that's really a sore spot for people on this test, but we'll address that too. That's kind of hard to wrap your brain around, and it really easy, even if your brain is wrapped around it. But really, honestly, right now, I just want to troubleshoot. So you had that probability part 1 last night. Were there any questions on that part 1 that you have questions about, you want to look at? I know some people right now traditionally have issues with, wait a minute, why are you using combinations sometimes? And then why are you writing out all the individual probabilities other times? And that's something we can talk about today too. If you don't have questions, it's child's play. We can move on to part 2 and still look at these things.
Can you do number 20?
Sure. This one?
Yeah.
Okay, so whenever you see the word at least, it's a big deal that you catch and lock onto that at least, because what might come into play is the complement. Okay, sometimes the complement will make your life much easier. People that go, no, I don't like the complement. I don't, and if you remember what the complement is, it's that whole idea of finding the probability that something happens is the same thing as 1 minus the probability that it doesn't happen. So for instance, me finding on number 20, me finding the probability that I get at least 1/5 would be the same thing as me saying 1 minus the probability that I. So if it's easier to find out the probability of not getting any 5s and then subtracting it from 1, if that's easier, great. Because what's the probability of getting at least 1/5 mean? I could have, well, I'm only rolling the dice twice, right? So it's not like I rolled the dice 18 times. And then me saying the probability of at least 1/5 would be, well, I could get 1 5 and 17 non-5s. I could get 2 5s and 16 non-5s. I could get 3 5s and but the fact that I'm only rolling 2 die, at least 1, well, really think about what that's saying. At least 1 means I'm getting a 5 and a non-5, or what? I'm getting 2 5s. That's really what I'm asking here. So what's the probability that I get a 5 or a non-5? Now, is this dependent or independent? So you have no chance of using combinations or permutations. You're going to have to look at each probability individually, okay? And then multiply them together, which is what the fundamental counting principle tells us to do. All right, if I could count these, if it was dependent and I could count them a different way, combination's great. No shot of that here. So let's just look at the first thing. What's the probability of getting a 5? 1 in 6. So I write 1 in 6 for that. And then what's the probability? 5 out of 6, right? You with me on that? So that technically is the probability of getting a 5 and then a non-5. But I didn't say that it had to be in that order, did I? So now what you have to do is say, well, how many different orders, even though the order doesn't affect the actual outcome, because there are lots of ways it could happen, not lots too, but because there are different ways it could happen, that's going to increase life affect the probability. So when I look at this, I could get a 5 first and then a non-5, or what? I could get a non-5 and then a 5. And that's two different ways. But if you think about it, it's kind of like saying how many different how many different ways can I organize the letters in FN? Like, and if I had those two letters, there's 2 factorial ways to arrange them. Now, we learned, like in Mississippi, you go back and divide by like 4 factorial for the 4 I's and 4 factorial for the 4 S's and 2 factorial for the 2 P's. We went back and did that. Well, here, I just get in the habit of saying, if there's 2 letters, 2 factorial, and then 1 of each, 1 factorial, 1 factorial. And I start building that habit. And that little thing right there, if I were to say that and then that in that order, because you don't have to count the different orders. And you don't have to do this right here if you're using combinations, because it's already built into the combination. It's already in there. And I think I did that. I broke up a combination and showed you how when you change it to factorials and remanipulate it and cancel, it ends up giving you this stuff right here out front, because that's built into the combination. And I can show you that again a couple times or whatever. But that would be the probability of at least 1 5. A 5 on the first or a 5 on the second. All right, you're counting both ways. That ends up being 2. Now, right here, for a 5 and a 5, what would you have? What's the probability of each choice there? 1 6 1 6. And you're welcome when you see 1 6 twice like that, just to say squared, or if it makes you feel better to do that, great. And on this one, or means plus. I could say 2 factorial because there's 2 letters, but because I would have to divide by 2 factorial, well, that cancels and gives you 1. So it's really, so that would be the oh, by the way, this is the probability of doing it. Are you with me? Now, when you're done with this, this says find the odds. So for me, I think in terms of probability, and when I'm done, I change it to odds. Now, there are better ways or simpler ways to do this particular problem, but I'm trying to show you this mentality so that when I say, it says essentially, if I said I'm throwing 20 dice, what's the probability of doing that? It becomes much more difficult to think when you have a lot of different dice that are being thrown without thinking this way. Like, I think on my notes, it might be something really simple that I'm actually doing here, a lot more simple than this on my key. But to me, that's the best thinking right there, and that will allow you to advance when it starts getting more difficult. Just this. So in this case, I probably want to simplify this because I need to kind of find odds. So this ends up being what, 10 over 36, and this ends up being 1 over 36. So you have 11 over 36. That's at least 1 5. And if it's 11 over 6 is my probability, if that's the probability, then what would the odds be? You remember how to deal with odds? Yes. And this is success plus failure, which makes your failure 25. So we'd say 11 to 25. Go with me? So that's what I would do on this. And I think if you start thinking this way, but that the word at least, instead of saying at least, I could have said, well, why don't I just go 1 minus no 5s? If I do 1 minus no 5s, or 2, the complement of that would be none. I'm sorry, 1 minus none. So no 5s would be what? What's the probability of getting no 5s? 5 over 6 times 5 over 6, right? So I get 1 minus 25, 36, which gives me 11, 36. So you end up getting the same thing there. If you want to think that way, it might have been a little. Whenever you see that word at least, that complement's in play. I mean, it's not just with at least, but it really is helpful with at least. Because again, what if I had said thrown the die 5 times? Now you got to talk about, well, I could have had 1 5 or 2 5s or 3 5s or 4 5s or 5 5s. That's a lot of different probabilities you're going to have to do. It'd be a whole lot easier to go 1 minus no 5s. Y'all seeing that? So you're going to keep seeing at least intermittently through this. and I might have done this. I might have done this. I might have used some other option. But the uglier it gets, the more you're going to need to be able to think in terms of these factorials right here. And if you're wondering why I didn't put that here, no fives, surely that's like saying no 5, no 5. 2 factorial over 2 factorial. It just would end up canceling. And the more you can start thinking that way and putting these numbers out front to count the different ways it could happen, or the different ways it could, the better off you're going to be long term on this. All right. Anybody else on anything? I think on part 2, you're going to see a little bit more of the same. All right. So let's just run to part 2. Part 2 is going to build off a lot of what you had here. Probably mix some stuff up. So you're going to see a little bit more here. But the big thing on part 2 starting out, it's probably part 2, is we're talking about independent. It's what we just did right here. So this is an example of a Tarzan. His batting average, if you know anything about baseball, and I'm not using strict rules of baseball like sacrifices and things like that. We're just going to play kind of, you know, if you get a hit, if your average is 0.3, that means there's a 0.3 or a 0.3 chance that you get a hit, which would mean not getting a hit would be a 0.7 chance. I mean, again, now rules like that would change that up a little bit, but we're going to ignore that. So we're going to assume that if you get 3 hits for every time, 10 times at bats, that's a 0.3. We're going to assume that if you don't get a hit, the complement would be that value. So if a 0.3 is getting a hit, a 0.7 would be not getting a hit. And you would have to figure that part out. So the question is, it says, what is the probability that he gets 3 hits for his next 5 at bats? So that's saying hit, 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 out, out, or non-hit, non-hit. Now, if I write hit, 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 out, out, why would that be wrong for my probability? What is this essentially saying? I would have to do it in that order, right? Get a hit, get a hit, get a hit, get it out, out. But if I say you're going to get 3 hits in your next 5, lots of different orders, right? And you can bother to write them all out. In this case, you could actually do it. There are 10 of them. Wouldn't be that fun to do. But a better way to think about it is, if they didn't specify that it had to occur in that order, you can just look at this and say, this is like arranging the letters in the word Mississippi. You can just come out front and say, well, there's 5 letters, but there's 3 of one kind, 2 of another kind. And when I do the math on that, which you won't have to do on this test, except maybe once, when I do the math on it, and you'll get that real simply. And you don't have to simplify it. You can leave it just like this. But in a situation like this, why, and this is where it's a little bit hairy here, why can I not use combinations or permutations? It technically isn't independent. We got a lot of baseball players in here up to bat, and you get a hit or you get an out, your batting average is changing. I mean, you're probably not walking in the dugout calculating it. Although when I was a kid, I used to do that. I think I broke 400 or whatever. But I would go home and try to do that, or whatever, sit around and try to do that, at least early in the season when I had limited at-bats. But the problem is, I don't know how many at-bats I have. Do I? All I know is that my batting average is this. I don't know enough to be able to say, well, after he does this, has his batting average changed? Yes. Do I know enough information to be able to calculate that new batting average? No, because I don't know how many at-bats. This could be 1,000 at-bats. And 1,000 at-bats, this game's results is probably not going to affect my average significantly. If this is early in the season, I've only had 10 at-bats, and all of a sudden I go 3 for 5, and now I'm 6 for 15, that's a much different result. That's going to significantly, well, maybe not significantly, but it's going to move my average a lot more than it would be later on the season when I had more bats. So because of the nature of this, even though technically it is a dependent situation, getting up there and playing and having at bats, I don't have enough information, so I have to treat it like an independent one. And if I treat it independently, then I can't use combinations of permutations. So again, I'm forced to look at each individual situation to read, because sometimes I'll say, hey, what's the probability that he gets 3 hits and then 2 outs in his 5 at bats? And if I say words like and then, I'm specifying what? That particular order. So what do you not do? You don't do this. And if it was a dependent event, and I said in that order, think about this question. If it's dependent, maybe it was picking cards out of a deck or whatever. If it's dependent and I specify order, can I use a combination? We said you could use combinations and permutations when it's dependent. Now, if the order that if you're playing cards and the order typically doesn't have an effect on the outcome, yeah, use combinations if you want. But if I specify the order has to happen in a certain way, it came from the part of the combination that was different than a permutation. So if that was the case, if I specify order in a dependent event, you would just use permutations. Or write it out like this if you want. You can always write it out with individual fractions for your choices. The problem is what happens when you start making 60 choices or 70 choices. Well, that's a lot of fractions. I would rather not do that. Are you seeing this right here on the? So when you're independent, you've got to make that decision and you've got to lock in and decide, okay. And by the way, you don't have to write 3/10 3 times and 7/10 twice. You can write 3/10 cubed, 7/10 squared, and it'll really shorten the process when you have these independent situations. All right? All right, let's take a look at some of these. So what about, and it talks about independent and dependent here again. What about these? We're going to solve them. First, you got to decide, is it independent? There are 2 cups of coffee, 4 cups of tea. Dave drinks 2 of the cups. What is the probability that the 2 he drinks are coffee? Dependent or independent? I certainly hope dependent, or he's drinking them and back into the cup. All right. So we're not doing any replacement here. That would be bad coffee house practice. Okay. So right here, I want the probability that I get 2 cups of coffee. So probability, because it's that I can't use combinations or permutations. All right. So I want the probability that I get 2 cups of coffee. I'm going to have to think about it independently like this. So what's the probability that I get a cup of coffee if I'm just blindly grabbing a cup off the counter? First cup, 2 out of 6. Second cup. Oh, wait a minute. What am I talking about? Yeah, this is dependent. I'm sorry. This is dependent. So I can use combinations of permutations. Sorry. My bad. It's dependent because I'm not, like I said, putting it back into the cup when I'm done. And I can, but I'm going to show you both ways. I'm going to show you I can do it individually with fractions, or I can do it with a combination. It would be your call on that. So 2/6 chance on the first choice. On the second choice, what? 1/5, because there's one less cup, period. Now, I'm going coffee, coffee, right? So technically, I don't need to use that part out front because the part out front would say 2 factorial, but there's 2 cups of the same thing, 2 factorial. And we know that 2 factorial with 2 factorial is 1. So whenever it's all of the same choice, this is kind of optional, but if you want to get into a habit of putting it there, put it there. And then the other option would be to say, what? I could say there are 2 cups of coffee. I'm choosing both of them over what? 6 cups of stuff, coffee or tea, which I'm choosing 2 of. And if you do the math on this, check it out. You get 2 factorial over 0 factorial, 2 factorial. Here you get 6 factorial, 2 factorial. And if I multiply by the reciprocal, move that up. Look how that simplifies. The 2 factorial right here is 2 times 1. That's that right there. And then you have a 2 factorial out still on the bottom. Here, 4 factorial over 6 factorial leaves me 6 times 5, right there with the 2 factorial on the top still. Thing as doing it this way, but it does it in a kind of a simple, compact way. And I can do that because it is a dependent situation. I'm drinking them and not replacing them. And I don't mind which way you do it. I know some people are like, I'm doing it like this all the time. Well, I'm probably going to give you a problem where you're going to be making 70 choices. If you're making 70 choices, like I'm going to give you something like, I don't know, make something up like there's, you know, some people wear tennis shoes, some people wear sandals, blah, blah, blah. What's the probability that if I choose 60 people, 40 of them will have tennis shoes, 15 will have 10 or whatever, and 10 will be barefoot, whatever. I'll give you something where if you're writing this, you're going to go, holy crap, I got to write 60 little fractions out. And that's not fun. But if I was doing combinations, you'd be saying like 60C20, 40C10. I mean, it would be a much simpler process. All right, what about this? 5 oranges, 4 tangerines. Beth selects one, replaces it, selects another. What is the probability that both are oranges? What do you got going on here? Replacement. What do you always know about replacement? It's independent. If it's independent, what can you not do? Combinations or permutations. So those aren't even on the table. So I'm going to have to go individual fractions. Orange. So what's the probability that I get an orange? 5/9. What's the probability that I get an orange on the next call? 5/9, which you are welcome to say 5/9 squared. So that's orange, orange. And then how many different ways could I do that? I could say 2 factorial, but there's 2 O's, 2 oranges, so I'd have to divide by 2 factorial. So technically, there's just one way to do it. Right? One way to do that situation. So again, that would be optional out front. All right, what about number 3? What's the probability if I throw a green die and a red die, that a 4 shows on the green die and a 5 shows on the red die? Dependent or independent? Independent? Because like whatever shows on the green die, I'm not gonna go, oh, 4 and a 4 on the red, right? They're totally independent of each other, those 2 die, and the numbers on one can continue to re-show. What's the significance of red and green? Well, yes, maybe.
They're 2, like, the order does matter, or not the order?
It basically says order. Like, for instance, what if I said they're both red? If I say they're both red, couldn't I get a 6 on this red, or a 6 on this red, and a 4 on this red? Are you with me? So if they were both the same color, it seems like it'd be a little bit different. But with the red-green, it's kind of like specifying some order here. So if I say, what's the probability that 4 shows on a green die and 5 shows on the red die? Let's think about this. So probability that 4 shows on the green is 1. So that's a 4 on the green. And then on the red, what happens? 5 shows on the red. What's the probability of that? 1/6. Now, that's it. It's almost like specifying order, because I can't say I have 2 die, what's the probability of getting 4 on one and a 5 on the other? I can't get 4 on the red and 5 on the green. So doing this is almost like specifying, hey, you can only get this or this. This is not going to come into play. I'm not going to go times 2 here. Are you seeing that? Because there's only one way to get a 4 on a green die and a 5 on a red. There's only one way. If they were both red, I could say, well, I could get 4 on this one, 5 on this one, or 5 on this one, or 4 on this one. But that's not true here. I can't switch this up and say a 5 green and a 4 red. When you're moving forward with this, put a star or whatever you want to by this, but make sure you kind of associate with, if I specify color with a number, you can't just switch the options. You're kind of locking in, hey, it can only occur like that or that. It's kind of like saying that the order matters here. It's kind of basically turning it into a situation where you don't have to worry about counting that stuff up. All right, Barbie and Ken are playing backgammon. The odds are 4-3 that Barbie will win. What is the probability that Ken will win? Now, remember what I talked about odds. What do you do when you see odds? Our brain and all of our rules think in terms of probability. So if I give you odds, Barbie will win. So Barbie winning, right? The odds that Barbie wins 4-3. That means there's win, loss. So what's the probability? Wins 4 and 7. Okay? Now, if the probability that Barbie wins is 4 out of 7, what's the probability that Ken wins? Which is the same as she losing, right? You with me on that? So probability that Ken wins would be 3/7. You can also think about that as the probability of Barbie losing is 3/7. So the question is, what's the probability that Ken will win the next 4 games? So I want to know what's the probability that Ken wins, essentially. Well, what's the probability that Ken wins the first game? 3/7, and then the second game, and then the third. So you don't have to write it 4 times. What could I say? 3/7. But again, this is saying W. So do I have to count the different ways that W could be arranged? Technically, yes, but technically, no. Because when I do that, I write 4 factorial over 4 factorial, right? Which is going to cancel and leave me 1. Now, it gets trickier when I say, what's the probability, this is not this question, but what's the probability that Ken wins 2 of the next 4? So that means win 2, lose 2. Then what would you do in a situation like this? He's got to win 2, which would be what? 3/7, 3/7, or 3/7 squared. And then, so that's win-win. Then he's got to lose 2, which would be 4/7, right? That's Barbie winning. 4/7, 4/7. Right? But if I just stop right here, what did I calculate? The probability that he did what? Won the first 2, lost the second 2. Did I specify that? Now I might, in fact, I totally will on your test. I'm going to give you a little bit of everything. So if I said that on the test, hey, wins the first 2, loses the second 2, done. But if I say just wins 2 out of the 4, then you got to count the different ways that could have happened. How do I do that? 4 factorial over. Like I was making new words out of Mississippi, right? So if the order was specified, leave that off. If it's not specified, you got to count that. And if it was a dependent situation, I could have used combinations, right? And combinations already has that part in the problem, and you don't have to worry about adding it on to the end. Number 5. Got 4 red, 4 green, 7 blue. What is the probability of getting a red, and then a green, and then a blue in that order? Now, well, first thing, I'm sorry, without replacement. What does it mean if I say without replacement? It's dependent. If it's dependent, can I use combinations or permutations? Yes, I'm going to do it both ways. If I used if I wanted to use combinations or permutations, why do I have to use a permutation here? Because it says in that order, okay? So what I would say is, okay, I'm picking 1 red from the 4 reds. So I could say I'm picking 1 of the reds. Basically, I'm counting how many ways I could do this. All right, 4P1. And then I'm picking 1 green. 1 green would be 4P1. And then I'm picking 1 blue. 1 blue would be, 7P1. So I'm picking for 1 of those 7. And I'm picking what? 3 from the 15. Now, do you know what this math is saying? Remember I told you another way to think about a permutation? I mean, you can use a little formula, But do you remember the shortcut way to think about it? This is the first number in 4 factorial, the first number in 4 factorial, the first number in 7 factorial, and the first 3 numbers in 15 factorial. So if you remember in 4 factorial, it's just 4. First number in that one, just 4. First in that, just 7. First 3 in that, 15, 14, 13. And when you think about the math of this individually, when you don't use permutations, isn't there a 4 out of 15 chance that you get a red? And then a 4 out of 15 that you get a blue, a green, and then a 7 out of 13 that you get a green, a blue. So this is going red, green, blue. And why don't I need to put this stuff up front? Because I specified that particular order. That's the only way it can happen. There's only one way to go red, green, blue. To arrange those 3 letters. And if I didn't specify in that order, I would have to put what out here? Tell me. 3 factorial over 1 factorial, 1 factorial, 1 factorial. And then I would have to change this to what? Yeah, because by changing this to C, do y'all remember the difference between P and C? By changing this, think about it. Another way to write this is this: 4 factorial over the difference 1 factorial. 4 factorial over the difference 1 factorial. 7 factorial over the difference 1 factorial. Now, these all cancel and leave me 7, right? But what I didn't really think about is it also left these 3 things. And on the bottom, this is 15 factorial over 12, 3 factorial. And this, the 12 and the 15 cancel, left me 15, 14, 13, but also it left this. Well, do you see that if I said something about, this is if it was combination. I'm talking about combinations. So if you think about the difference between a combination and a perm, difference is those numbers right there, when you multiply by a reciprocal, end up giving you the 3 factorial and the 1 factorial, 1 factorial, 1 factorial. You see that? Those right there, those extra numbers you put in there for a combination. And when I have a permutation, I go back to where I was, it just gets rid of those. The permutation definition just doesn't use that. With permutations, it doesn't have that junk out front because it didn't have that extra part of the definition. You got tracking with me on this? Okay. Look at this one. Bad contains 5 red, 4 white, 7 blue. 3 are selected in succession. What's the probability that are red, white, and blue in that order? No replacement. It's dependent. Okay, now if it's dependent, can I use combinations or permutations?
Yes.
Yes. Which one would I want to use here? A permutation, why? Because I said in that order. Now, do I have to use a permutation or can I still use the fractions? Yeah, you can always use the fractions, whether it's dependent or independent. Always. Sometimes it just takes a lot of work because there's a lot of choices, but not in this case. So we're going to do this 2 ways. Replacement. So I'm going to show it with the permutation first, and then I'm going to show you with fractions. And then when we go to this, you'll see that with replacement, I don't have the option of a permutation. So right here, red, white, and blue in that order. So this is me picking a red, a white, and a blue. So picking a red, I would say I'm picking 1 of the 5 reds, 5 P1. I'm picking 1 of the 4 whites. I'm picking 1 of the 7 blues. Did I just do this?
No.
Feels very similar. 7 P1. And I'm doing this out of what? 16 P3. Now, if I think about this as one choice at a time, what's the probability that I get the first red marble? How many with this bag and grab a marble that it's red? 5 out of 16. What's the probability that the next one, again, this is red, white, blue, a different way. Probability that the next one's white. 4 whites out of the remaining 15. What's the probability that the last one's blue? 7 blues out of the remaining 14. Do you see that this right here means the first number in a 5 factorial number in a 4 factorial, that's 4. First number in a 7 factorial, that's 7. First 3 numbers in a 16 factorial, 16, 15, 14. It's the same thing. And why don't I count the order out front? How many ways that could be ordered? Because it's specified in that order, which is the same reason I can't use C's here. Right? What about this one? Replacement occurs. So what changes in this model here? I have no option to do this, do I? So, and then what changes here? I can't use this anymore, but what part would change? The denominators, right? Because I'm putting them back, and if I'm putting them back, I still have 16 each time. Now, there's still only 5 reds and 4 whites and 7 blues. So that part, 5, 4, 7, that part didn't change. But 16, that part stayed the same as I was putting it back in there. Right? Tarzan's got a batting average of 300, which means he gets a hit, like we mentioned before, 3 times every 10 at bats. What's the probability? I'm jumping to number 12. What's in the next 10 at bats? Now, every year I have somebody who goes, well, if he has a 300 batting average, that means he gets 3 hits in the next 10 at bats. So 100%. Now, if you played any baseball, you know that if you're a 300 hitter, there is no guarantee you're going to get 3 hits in the next 10 at bats. It means that's the most likely probability of the result of your next 10 at bats. All kinds of things can happen, right? So there's no way, even if that's your batting average, that's just a predictor. So how do I figure out 3 hits in 10 at bats? First thing, is it dependent or independent? We have to treat it like it's independent, right? So no combinations. So I got to do individual probabilities. What's the probability that I get a hit? 3 in 10. What about another hit? 3 in 10. Can I just go that cubed? What's the probability of not getting a hit? I'll call it an out. 7 in 10, right? But I got to do that 7 times. Do I stop here? When would I stop here? If I said your next 3 at bats were hits and then your last 7 were outs, then I'd stop. So 10 factorial over 3 factorial, 7 factorial. And if you do the math on this, you get 10. You get just so you can see it. Seems like it's 20%. Yeah, 27% chance, 26.7. So there's only basically a 1 in 4 chance that you bat your average. But that's the highest percentage of all the other options. But there's a lot of other options, right? You could go 2 for 10, 6 for 10, 10 for 10, 0 for 10, 1 for 10, 7 for 10. There's lots of different ways you could do it. The greatest chance then would be, because that's your batting average, that's the greatest probability. There's a 1 in 4 chance that happens. But there's a 3 in 4 chance that something else happens. How about jump to something else? How about this? Chance of rain each day of this week. Let's just say it was given to be 25% all week. Given that, what's the probability that it rains on 3 days out of the 7? Now, 25% is basically what? 0.25. You can always move the decimal and call it 0.25, but if you want to do 1/4, that's great. If I had to multiply it out manually, which you don't have to, I'd probably use 1/4 because that's probably easier for me to deal with that. But again, 25 or 1/4 or 0.25 or 1/4 is fine. So I want rain 3 out of 7. So that's rain, what? 3 times. What's not rain? 0.75, and that would be finished. Because it didn't say 3 rains, 4 not rains. It says 3 out of the 7. So what goes out front? Not bad. How about jump down to 18? Standard deck of cards contains 4 suits of 13 cards each. What's the probability of drawing 13 diamonds? Between the word suit, that's important that you recognize suit and recognize kinds, or suits and kinds. When I'm talking about suits, I'm talking about what? Hearts, diamonds, spades, and clubs, right? And when I'm talking about kinds, I'm talking about, right, kings, jacks, 10s, 7s, aces, right? Probability of drawing 13 diamonds without replacement, if I'm not putting it back, is that dependent or independent? Dependent. If it's dependent, can I use combinations or permutations? Yes. So if playing cards, it doesn't specify. I'm going to assume that that the order in which I take them doesn't matter. So how would I choose? I'm using combinations. What would I say? What am I essentially doing? I'm picking 13 diamonds from the y'all just staring at me.
Okay.
Now, if I want 13 diamonds, I want to count the number of ways to be successful over the number of ways to just draw 13 cards. To be successful, I have to pick, think about it. All the cards are down here on the floor, face up. And I say, come down here. Are you going to walk over here with your head up and just grab 13 cards? Not to be successful, you're not. To be successful, you're going to look down and your eyes are going to lock in on what? Diamonds. So really, if I'm counting the number of ways to be successful, I'm picking the 13 from the 13. So I got to say, all right, there's 13 diamonds. I'm picking all 13 of them. Now, when it comes to actually how many ways, I'm picking 13 from the what? From the deck, from the 52. Now, that's using combinations. But I can still use fractions, right? I can always use fractions, except there's going to be a lot of stuff to write out on this one. So let's think about it one at a time. What's the probability that on your first choice, you get a diamond? First choice. 13 out of 52, and you could write 1/4, but I don't. Kind of line up for me. What's the probability on your second choice that it's a diamond? 12 out of 51, and on your third, like you don't have to put parentheses around all these. So you have 13 out of 52, 12 out of 51, and then 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, because you're picking all 13 of them. 51, 50, 49, 48, 47, 47. Y'all see this? Now that's diamonds all the way. So, and it doesn't specify in that order. So technically, for me to do diamond, think about it, I guess like with the D. For me to do diamond, 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 all the way there, you're kind of saying, well, it's 13 factorial over 13 factorial. Which, let's be honest, is kind of unnecessary, isn't it? Yes? No?
So,
Yes.
if the order doesn't matter, wouldn't that mean there's like more possibilities, but then multiplying it by 1?
Yeah, but yes and no. Because all of them were diamonds. That part canceled. And if that part canceled, that's the same thing as using a permutation. You end up picking all diamonds, it's nothing but D's, right? Changing the order doesn't do anything, right? So in this case, the permutation combination is the same thing. think of the math on this. The math on combinations right here would be this. 13 factorial over 0 factorial with an extra 13 factorial. Here, 52 factorial over, 39 factorial, 13 factorial. Look, those cancel. Those right there cancel. Isn't that the only difference between a combination and a permutation? Is that extra part there? So in this case, it's kind of the same. But the second I go, hey, what's the probability of drawing 10 diamonds out of the 13? Now the arrangements start to make a difference. And then combinations has to be used. So if you had accidentally used a P there, I would have to count it right. Even though technically we're playing a card game where the order doesn't matter. Because your math's right. If you did put this, technically it's still true.
Is an ace a face card?
No, a lot of people ask that question. Face cards have faces on them. So,
Yeah, because isn't there only 12?
Yeah.
yes. So wait, what's the probability of drawing 13 face cards?
21.
What's the probability of drawing 13 face cards? 0. Don't write, it's impossible. Literally, if it's an impossible event, in our notes, we define that as a probability of 0.
I didn't want to be dumb and be like,
Hey guys, do your best on this, and please bring questions in when you're looking at something and you're like, I don't know why you did that, or I did it differently. Remember, my P's don't always write it both ways, okay? So if you have a question and you're not quite sure that you're doing it right, feel free to ask. Is everybody here today?